Hello, students. Today we want to talk about two very important one-to-one functions. They are the base A exponential and the base A logarithm. In the last lecture, we talked about one-to-one functions, their definition, how to show that a function was one-to-one, and then compute its inverse. For this particular lecture, we do not have the means at this point to show that the base A exponential function is actually one-to-one, but we will make that assumption and we will use its properties to define its inverse function, which is the base A logarithm. When you get to the calculus, you will have a mechanism to actually provide the proofs for one-to-one. That is, you will start with the natural logarithm and then transfer that information into defining the natural exponential. That will be a more sophisticated way of studying those functions. However, we want to go ahead and look at many of the properties of these functions because they are necessary ingredients for you to understand the calculus when you get to those functions. So let's go ahead and get started. Let me share my screen. Now, when we think about the one-to-one function, again, we think about the simplest kinds of one-to-one functions. That is when we have increasing or decreasing. Again, in many instances, algebraic functions, we can actually show that we do indeed have a one-to-one function. But what's different about these particular types of functions is that they are no longer algebraic. They are termed transcendental. So they have many of the algebraic properties that we utilize daily. However, they have significant differences that require a more sophisticated approach when we're trying to prove things like one-to-one. But that's not going to deter us, and we're going to be able to do much good mathematics. Now, what I have here is a summary sheet that I want to share with you because it provides many of the foundational qualities for the base A exponential. And then again, we will transfer that to the inverse function, which we will call the base A logarithm. Now, what we're going to do, ladies and gentlemen, is start with a base, and that will be a positive real number, which we can call A or any letter you like. Usually we'll use A just for convenience, and the A will be non-unity. We don't really want to utilize a base of 1 because powers of 1 are just 1. So that doesn't really help us out much. 1 is the multiplicative identity. So we will avoid that. So the real number A is called the base. Again, base A exponential. Now, when we define the base A exponential, it will remind you of the power function. That is, in this case, instead of the base being variable as we have with the power function, the base will be the fixed number A, and the exponent or the power will vary. So that's why we say base A exponential, and we will define this for all real x. Now, what will be a little surprising to you is that the base A exponential will have what we call exponent rules that mimic the power rules that you are accustomed to with power functions and algebraic functions. So that will make our work a little easier. Now, for starters, we're going to assume that x and y are real numbers, and we are going to define a to the 0 power to be 1. That is, when we have 3 lines here, we assume that to be a definition. So a to the 0 is 1. 3 to the 0, 1. Pick your favorite a, raise that to the 0 power. By definition, we have 1. I'll say why that has to be that way when we get to one of the lower rules here. Now, one rule that will be very familiar to you is that if you multiply two base A exponential functions, you can actually add the exponents, just like the power rule for algebraic functions. Now, again, in a very similar fashion, if you divide two base A exponentials, you can subtract the exponents, the same as you would do for power functions. Now, this is exactly why we define a to the 0 to be 1, because if you notice here, if we divide a to the x by a to the x, that by definition is 1. But then if we apply this rule, subtracting x from x, we get 0. So a to the 0 must be 1 if it's going to be consistent with rule number 3. So we have no problem deciding on this definition. So again, be sure to use that in your calculations. Now, another useful exponent rule is that we can raise the base A exponential to a power y, or to another exponent. Notice when you talk about exponents or powers, those words can be interchangeable. So don't worry, just pick one that you find to be convenient. So now we raise the base A exponential to the power y, and we simply multiply the powers or the exponents and get x times y. And that becomes the new exponent or the new power of the base A. So again, these should be very familiar. Now, one thing that we notice by our definition, all real numbers will be the domain of the base A exponential. But again, we do not have all of the sophisticated mechanisms to prove certain properties. And so one other property that will be very important is the range of the base A exponential, which will be all positive real numbers. So what's interesting about the base A exponential is that we have different sizes of bases. That is, when the base A is larger than 1 or bigger than 1, the base A exponential increases, as we see here. And then, of course, a to the 0 gives us 1 as the output. We get this nice increasing function. However, when the base is between 0 and 1, which again we can get through using negative exponents, we get a decreasing function, and it has this shape here. Again, exponential functions become large very quickly, and we need to be able to make estimations between algebraic functions and exponential functions when we get to the calculus. So that's exactly why we're talking about them now. Now, just as we did in the previous lecture, we know that since we are assuming that the base A exponential is 1 to 1, we can use the symmetry line y equal x to sketch an inverse function. Just like you do many times, as we did in the last lecture, we can use the line y equal x to draw a picture of the inverse function. And again, a very useful tool. So what we're noticing here is, again, the domain of the base A exponential is all reals, so the range of the inverse function will be all reals. However, the range of the base A exponential is just positive real numbers. That means the domain of the inverse function will only be positive numbers. So that's going to be very restrictive for the inverse function. We're actually going to call that the base A logarithm. And therefore, when we actually define it, the argument or the input of the logarithm must have a positive value. Now, of course, it can be an expression, but for the expression to make sense, the actual input or argument must be positive. So when we talk about domains of logarithms, we're thinking about all x for which the argument will be positive, and that will drive the definition for the domain of the base A logarithm. We'll say more about that. Now, one thing that we want to notice, which actually most of the functions we deal with, or actually all of them, they enjoy continuity. That is, we can draw the graph and it have no gaps or holes in it. Well, of course, we can think about rational functions where they have holes in them, but we think about asymptotes, vertical asymptotes. That's what we call an infinite discontinuity, where the function actually breaks apart. and it may rise to positive infinity on one side of the asymptote and then diverge to negative infinity on the other side of the asymptote. So again, we're going to assume the continuity and also the smoothness. Notice when we draw functions, we always usually draw them in a smooth manner. That's not because we're just making that up. That has to do with the properties of these functions. In many cases, we will have continuity or continuous functions where the particular functions are defined. And then for the most part of the domain, we will also have differentiability. And ladies and gentlemen, it's the differentiability that makes the drawing smooth. That is, when we have a smooth graph, we are basically exhibiting the differentiability of the function. But that'll be a big topic that you'll have when you study the calculus. We're just doing the preliminaries right now. Now, one other thing that you might notice is that for the base A exponential, we have the x-axis as a horizontal asymptote. So notice for the case where A is greater than 1, as x passes to negative infinity, the base A exponential approaches 0. Now for the case where A is between 0 and 1, as x approaches infinity, the base A exponential function approaches 0. So that's the difference between this case where we have an increasing function for A bigger than 1, and we have a decreasing function when A is between 0 and 1. So again, if you've noticed here, I've put some little notations here that we used when we talked about rational expressions that can be very useful when we get to the calculus. But for now, for instance, if you just look at a very simple example of the second case where A is 1/2, this is now a decreasing function. So as x passes to infinity, we would expect the limit of 1/2 raised to the x power to be 0, because again, decreasing, values getting closer and closer to 0 as the value of x gets larger and larger. Now, like I said before, we don't have the sophistication to prove that the base A exponential is 1-to-1. We will assume that. And because we have the 1-to-1ness, we have to use a symbolic gesture to define the inverse function. That is, this is not an algebraic function, so we will not formally solve for it. So we're going to use this set of symbols. That is, the base A logarithm will be the inverse function of the base A exponential. And basically what we're going to say is that y is the base A logarithm of x if and only if x is a to the y. So as we will see, the logarithm, or the base A logarithm of x, is just a power of the base A. So when we think of y as being a base A logarithm of x, it is basically the power of A that equals x. So we get x equals a to the y. So what we can think of in this particular case is, since we start with an exponential function and we want to think of a reverse path, we actually end up with the power of the base when we go into the reverse path. So that's why we're always going to think of the logarithm as a power of the base. We'll say more about that as we move through the lecture, but I want you to be very understanding of the basic properties that we have of the base A exponential. We will use these properties over and over, and I want you to practice with them. So let's do some of that. Now, I've got some examples here that I want us to go through. The very first one has to do with using properties to solve equations. Now, the base A exponential is 1-to-1, so we can use the 1-to-1 property to solve equations. That is, note the base A exponential function is 1-to-1. And you can abbreviate 1-to-1 by just doing 1-1 if you like. That's certainly okay. Or you can write the 1-to-1. That will be good. And what that means is that if we have a to the u equal a to the v, this will imply that u equals v. This is the 1-to-1 property. And then, of course, what this is saying is that when the bases are aligned, we can simply equate the exponents or the powers and solve the equation. Now, here's an example. We have 1/25 raised to the x plus 2 power. And this will equal 125 raised to the 2 minus 3x power. Now, when you look at this, you're thinking, well, this is very different from the types of equations that we saw previous to this. But by using the 1-to-1, we can actually solve this. Now, what this problem will require is that we're able to align the bases on each side of the equation. But what you can see is that the 125 and, of course, the 1/25 are actually powers of the base 5. So let's do a little observation here. And this will make the problem very easy. So we observe the following. That is, 125 is simply 5 raised to the 3rd power, and 1/25 is 5 raised to the -2 power. So this gives us powers of 5. So we'll say base equals 5. Now, when we can do this, we can use 1-to-1. You might be thinking, if that is not the case, what will we do? Well, we will have to use the inverse function. We'll have to use the base A logarithm. So the utilization of the inverse function will be something that we will often do because we won't have the luxury of having the bases aligned. So you can see this is a very unique type of equation, and it doesn't occur all of the time. And so even though it is fairly restrictive, it would be good to know how to solve it because these types of equations do arise. So now what we're going to do is substitute for these bases that we have here to write them as the very simple powers of 5. So on the left-hand side, we have 5 to the -2 raised to the x plus 2. And on the right-hand side, we have 5 to the 3 raised to the 2 minus 3x. So now we can just use the laws of exponents to multiply the powers. So we have 5, so we have a -2 times x, which is a -2x, and a -2 times a 2, which is a -4. Now, of course, we can do the same here. 3 times 2 is 6, and then 3 times -3x is a -9x. So when we look at this, we now see that we have the 1-to-1 property perfectly set up. We have the bases aligned, and then we can set the powers equal. So now we can use 1-to-1. So this says minus 2x minus 4 equals 6 minus 9x. So I'll write this to the side, 1-to-1 property. Again, we know that this is the definition of 1-to-1. So if we were assuming that the base A exponential is 1-to-1, we can make use of it. And we see how useful it is in this particular problem. So now we can isolate the x. So if you want to add 9x to both sides, you'll get a 7x. And adding 4 to 6, you get a 10. And then, of course, x is just 10/7. Now, the base A exponentials are very forgiving. We don't have the restrictions that we'll have for the base A logarithm because the domain of these functions is all real numbers unless we restrict it or if we have powers that restrict it. So now we can see that our solution set is simply 10/7. So again, by one-to-one, we can simply utilize our definition and the fact that we have the laws of exponents. So that's really critical that you utilize the laws of exponents, because they will allow us to ascend to this level, which is now very simple. Now let's look at another example. There are two bases that we will find that are very frequently used in STEM mathematics. One of the bases is called the natural base. Now, you may have seen this previously, but the natural base, again, is a transcendental number. It is not the zero of any integer polynomial. And so that means it's very distinguished. It's like the number pi from geometry. Its decimal representation does not repeat. And because of that, it has a very distinguished status. Now, you know, numbers like the square root of 2, they do not have repeating decimal expansions. However, they still have different properties, because square root of 2 is simply a zero of the polynomial p of x equal x squared minus 2. So it's very different from a transcendental number. So again, this will be something that you study as you take more mathematics when you get to the university. So the natural base we will denote by the letter E for Euler, the famous mathematician Leonhard Euler. And it will be actually a limit. The limit as, and of course, we can use n, we can use all kinds of letters. I'll use n because when we actually do compound interest, we'll use n for the number of interest levyings that we will have during the year. So maybe we'll stick with that. So we have n passing to infinity of 1 plus 1 over n raised to the n. Of course, you can use an x in the place of n if you like. Now, this limit is actually an increasing, that is, this particular function is increasing, and it is bounded above. So by the monotone convergence theorem, it actually converges. And the number that to which it converges, we just call it the symbol E, just like we use the Greek letter pi to represent the ratio of the circumference of any Euclidean circle to its diameter, just because it's more convenient to write a symbol than to just do a decimal approximation that could be difficult to use in calculations. So now what we do, we'll just go ahead and use some numbers that approximate this, 2.7182, and this goes on ad infinitum. So this is like pi, which is approximately 3.1416, again, whose decimal expansion goes on ad infinitum, never repeating. So these types of numbers have the same description. Now, there are an uncountable infinite number of these, but we don't spend a lot of time with them. These particular numbers are very important to us, and we use them quite often in STEM mathematics. So that's exactly why we're talking about this today. So this is a natural base. Again, this is a number that is bigger than 1. So this is an increasing function. So we have e to the x as a function of x is a very important increasing exponential function. So important increasing exponential function. So it has the standard shape that we saw on the previous slide, increasing, just like this. So this is y equal e to the x. And then, of course, if we were to draw the inverse function, the base A logarithm, it would look like this. And we could call this y equal the base A logarithm of x. Again, when it comes to functions, the reflective property is very useful to us because it reminds us of the interchange of the coordinates. So again, when we think about how things interchange, we can write down some very interesting results. For instance, notice here, we have the limit, just using the limit symbols, as x approaches negative infinity of e to the x would be 0, because y equals 0 is a horizontal asymptote. Now, of course, this is approaching from above, so we can put a little plus there. Now, equivalently, this is what's so interesting and so unique about the inverse function. Now we can say the limit as x, again, using the same independent variable, or again, when you take the calculus, you'll be more flexible about the x's and y's, more flexible, and maybe not interchange them as much and not always represent them by the same letter. It just depends on the discussion that you are working with at the time. So for instance, we could say x approaches 0 from the right or above of, in this case, the base e logarithm. So we do e to the x. There's another very convenient notation of this called ln, but I'm just going to use the notation I've given you. The base here is e, so we say base e logarithm. This would just be negative infinity. So what we're seeing is that the results just interchange. Here, x is approaching 0 from the right. Here, e to the x is approaching 0 from above. We just see that the zeros and the negative infinities just interchange. So that's the luxury that we get with inverse functions, and it's very useful and very helpful. So again, just remember that by the assumption that the base A exponential is 1-to-1, we get lots of results with that. We get the existence of the inverse function. We get all the properties that would result from that connection between the two functions. Okay, so let's now look at an equation that has our new base E. And of course, we could use the base of our number system, which is 10. That's called the common base. But we know a lot about 10. We've used it all of our lives. Base E is actually fairly new, and we want to be able to work with it. So let's look at another example. Say we want to solve the following equation. We have e to the x squared equals e to the 3x minus 2. Now, again, you're thinking this is so much easier than the last problem because, again, we have the e that's already aligned, and all we have to do is use the 1-to-1 property to set the powers equal. So this is ready to go. We didn't have to do any work. So x squared equals 3x minus 2. Now, of course, this transports us back to the first week where we were solving quadratic equations. So now let's just go ahead and transpose. So we have x squared minus 3x plus a 2 equals 0. Now, of course, what we can see, AC is just 1 times 2. And now we can just append a negative to each of the factors to preserve the 2, but then the sum would give us the negative 3. So this easily factors. So we have x minus 1 times x minus 2 equals 0. And therefore, by zero product, we have x equal 1 or x equal 2. So again, it's very important to be able to set the powers equal. This is a luxury that we do not have without the one-to-one property. So that again, when we deal with functions that are invertible, we have many properties that we don't actually enjoy with other functions that do not have the one-to-one property. So now we have a solution set of 1, 2 for this equation. Now, one thing that's actually very important and that I want to remark about is that when we're dealing with graphs, we can now think of the parent function for the base A exponential as a paradigm, so to speak, as a model. So we can shift it, we can stretch it, compress it, do those types of transformations to get a graph fairly easily using transformation techniques or transformative techniques, because functions that we deal with, again, when we do transformations, those are universal. So whatever new function we have, we can apply the same results. So here's an example. We want to graph the following function. We have f of x equals 3 minus e to the negative x. Now, this is not very difficult, but the parent function is new to us. So what we want to do first is just to kind of rewrite this. We have negative, or the additive inverse of e to the negative x plus a 3. So we can look at this as two reflections and then an upward vertical shift. So let's apply this. So we have our parent function e to the x, and then we can just do the x-axis. Oh, excuse me, let's start with the y. Let's do the y-axis reflection. Just replace x with the negative. So this gives us e to the negative x. And now we can apply the x-axis reflection. So what's interesting about this, and if you look at this, you can apply these in either order. That wouldn't matter. We could do the x-axis applying the negative to the e to the x, and then do the y-axis by replacing x with its additive inverse. So the order would be your choice. And then lastly, we'll just do upward v shift by 3. And let me, sorry, I'm talking about the function and I didn't leave any space, and I don't think I can squeeze it in there. Let me just go ahead and put this in. So we have the negative e to the negative x. Let me go ahead and put that in there. It'd be too hard to squeeze in. And now we have the upward v shift by 3. That looks a little better. So now we have the negative of e to the additive inverse of x plus a 3. Now, when you want to draw this, you can just use really simple parameters from the parent graph. So let's just remind ourselves that we have some really easy stuff going on here. So we've got the 0.01. So we have the point, like I write here, 0, 1, and we have y equals 0 as the horizontal asymptote. So let's go ahead and see what happens. So we'll move both of these. So we have 0, 1, and we have y equals 0. Now, of course, the 0, 1, we're doing a y-axis reflection. So we're replacing the x-coordinate with its additive inverse. So that's not going to change. And now, of course, we're again doing a y-axis reflection. And so the horizontal line will not be changed either. So we just have y equals 0. Now for the x-axis reflection, we're just replacing all y coordinates with their additive inverses. So this will be 0, -1. And then, of course, we're actually reflecting this in the x-axis, but it's y = 0, so there's no change with that either. So not too difficult, but important. Again, y = 0 is just the x-axis. So if we're reflecting in the x-axis, that is unchanged. And lastly, we do an upward v shift by 3. So we'll add 3 to all the y coordinates. So this will give us a 0, 2. And then, of course, y = 0 becomes y = 3. So now we have a new horizontal asymptote of y = 3 and a new point, 0, 2. So let's go ahead and draw this. So we've got our x-axis. Again, like I always say, this isn't Rembrandt, it's just a reasonable facsimile. So we've got 1, 2, 3. So we have y = 3, and then we have the y-intercept 0, 2. I'll go ahead and do that in red. So now when you think about what's going on, we start out with this, and then we do a y-axis reflection that does this. Then we bring everything down and then move it up. So we've got something like this. So this gives us f of x equals 3 minus e to the negative x. Now, here's something that's interesting about this. We get a lot of freebies here. Notice, this makes perfect sense because we know that the e to the negative x is a decreasing function, because if we apply the negative, it just inverts the e to give us 1 over e, which is a number between 0 and 1. So for instance, e to the negative x, ladies and gentlemen, is just 1 over e to the x, because we're using the rule that says if we have a negative exponent, we can simply invert the base and then write 1 over e to the x power. So this is a decreasing by our characteristics of the base A exponential. And so now, as x gets really large, this particular function approaches 0. So we can see now that the limit as x approaches infinity, it just from an intuitive standpoint, which is very important, we have 3 minus e to the negative x would just give us 3. And of course, this approaches 0. So the limit would be 3, because we know that this is a decreasing function. And so our graph basically exemplifies that as x gets larger and larger. And let me just notate this is our x-axis and y-axis. We hug more closely the horizontal line y = 3. And so we never cross, but we have the asymptotic approach to the horizontal line y = 3. And we can see that this is verified by these calculations here. So when you get to calculus, the intuition that we build here will be very important. And again, we'll take all of this understanding, and then as we apply more arithmetic from the calculus, you will have a more thorough understanding. So again, just remember, when you're doing the transformations, the new parent function is now the base A exponential. And you can do the same thing for the base A logarithms. So we see here that what's interesting about this, and you're noticing here, we have to cross the x-axis right there. Okay, I'm just kind of like crossing the axis. We know we crossed the y-axis, but now this is basically saying f of x equals 0 if and only if 3 minus e to the negative x equals 0, if and only if, what does this mean? This basically says e to the negative x equals 3. Now, this is an exponential equation. Now you're thinking, well, we could try to change the base, but we don't have any change of base set up right away. And of course, if we did, we could rewrite that with a base e and then be on our way. But solving this equation basically tells us, okay, what's really going on here? I mean, how would we do this? Now, let me just show you a notation. Before, I said base e logarithm of x for the natural logarithm, in the sense we're using the natural base. The more used notation is just replacing log base e with ln. Now, again, since this is such a popular base, it gets a special symbol. You can certainly write base e logarithm of x, and it's very understandable what you mean. But due to the fact that the natural base has such a distinguished position in mathematics, we give it a special symbol and write it as ln of x. Again, lots of notation, lots of convention in mathematics. So now when we look at this, we're thinking, okay, what's a logarithm? Well, as I said before, it's a power of the base. And so we see that the power of the natural base that equals 3 is negative x. So negative x is a logarithm. So we get the negative x is the natural log of 3 using the new notation. And if we solve for x, we see that x is just the additive inverse of the natural log of 3. And that is our intercept here. So again, what's important here is, just by virtue of the fact that we have an inverse function, we can actually solve equations that really weren't presenting themselves in a way of a line basis that we saw in the previous examples. So again, the existence of an inverse function makes solving equations easier. And it's something we do all the time, especially with square functions and square roots. We want to undo squares, so we apply a square root function and an inverse function. If we want to undo a natural exponential, then we want to apply the inverse function, which is the natural logarithm. Okay, so this is the kind of schematic that we're interested in doing. So let's go ahead and say a little bit more about the logarithms. Now that we see there's a good reason to study them. So lots of students, when I tell them or I ask them, I'll say, what is a logarithm? And they say, well, Professor Ollis, a logarithm is a power of the base. So what we want to be able to do is utilize that in solving more equations, and also in moving from the logarithmic form to the exponential form. So as I said before, we'll say y equals the base a logarithm of x if and only if, that is, a logarithm is a power of the base. So a to the y would have to equal x. That is, the power of a that equals x is y. So a raised to the y power equals x. This is what we call log form. And this is what we call exponential form. Now, as I said before, the notation for the base e, that is, we have the natural logarithm of x instead of using base e log. Now, of course, when we have 10 to the x, you might be thinking we do the base 10 logarithm. Well, we also give a special symbol for that. We just call it log. So we don't put the 10 there. So if you have the absence of the 10, the assumption is that it's base 10. So this is the base 10 logarithm, the common base. So these are special symbols for bases that are considered to be distinguished in our mathematics. So again, base E logarithm is notated ln. The base 10 logarithm is notated log. So what we can do, I have several examples here from your lecture notes. Let's just practice going between the two. For instance, here are some examples that usually are good for students. So we have the base 3 logarithm of x equals 4. We have x to the 5th equals 12. And we have the base 3 logarithm of 8 equals 2. Now, well, in this case, let's just say here, let me actually write this correctly. That's x, which is a better equation to write. So we have the base 3 logarithm of 8 equals x. We have x to the 5th equals 12. And we have the base 3 logarithm of x equals 4. Now, what we want to do here is write the corresponding forms. So here, what's a logarithm? A logarithm is a power of the base. So the power of 3 that equals x is 4. So the power of 3 that equals x is 4. So 3 to the 4th equals x. That's the corresponding exponential form. Now, this is in exponential form. So again, one thing you can do when you actually think about this, you can think about taking the logarithm. Here, this says the power of 3 that equals x is 4. That's exactly what this says. Now, when you look at this, we're saying that the power of x that equals 12 is 5. So 5 is a logarithm. It's the base x logarithm. So we say the base x logarithm of 12 equals 5. So what's a logarithm? Power of the base. The power of x that equals 12 is 5. That's exactly what this says. Again, what's a logarithm? Power of the base, because it's the reverse path. Now let's do this one. Again, what we have here, we have the power of 3 in this particular case that equals x is what? Excuse me, the power of 3 that equals 8 is x. X is a logarithm. So we say 3 to the x equals 8. So again, if you take the base 8 or the base 3 logarithm of this, you basically get x equals the base 3 logarithm of 8. So again, what is a logarithm? It is the power of the base. And so if you think about this mechanism, you're basically defining in a mechanistic way. That is a way to solve equations. That is, this is not the most sophisticated way that we would think of defining exponential functions or logarithmic functions. But when we think about tools to solve equations, this is actually ingenious. Because again, by interpreting the logarithm, the base A logarithm, as the power of the base, it allows us to move between each of these depending on what the scenario may be. So again, practice this, teach this. It's not difficult. It's just reminding yourself of the reverse path. Now, let's write down some domains. I have some examples from your lecture notes, but again, as you practice this, remind yourself every time you look at an equation, no matter how simple, use the power of the logarithm definition that we've agreed upon now to solve it. So let's look at some simple examples here. Let's say we have f of x equals the natural log of x plus 1 divided by x minus 2. And we want to compute the domain of f. Now, as I said before, if we remind ourselves of the actual range of the natural exponential, it's all positive real numbers. So that becomes the domain of the natural log. So basically, this expression must be positive. Just recall, the range of the natural exponential is all real numbers that are positive. So this necessarily becomes, in this case, the domain of the natural log. Just like what we did when we talked about one-to-one functions. So the domains and ranges just interchange. What's a logarithm? Power of the base. So now this will say the domain of f will be all real numbers x such that x plus 1 divided by x minus 2 is indeed positive. And you're thinking, boy, we'll do these simple inequalities any day. I mean, they're so simple that no factorizing necessary. Everything's set up for us. So equivalently, we'll just say our BVs, where's this undefined at 2? Where is it 0, negative 1? So we just do our number line with multiplicities. These both have multiplicities 1, so we know the sign will change on either side. So we'll just take 500 for x, where this is clearly positive. So we change sign, and then we change sign again. So here we have plus above, just like we did when we were graphing the inverse function, negative below, and then positive above. The multiplicities are so instrumental in giving us an efficient technique to solve inequalities. And so now we just look for where this particular expression is positive. So this will imply that the domain of f will be all real numbers, negative infinity to negative 1, union 2 to infinity. So what we're seeing here, ladies and gentlemen, is that if we just look at this, this is a very simple inequality. And now we actually couch this into computing the domain of a logarithm function, because this becomes the argument of the logarithm function. It must be positive. It doesn't mean that the values of x can't be negative. It just means when you substitute them into the expression has a positive sign. Okay, so again, the beauty of all of the work that we've done to this point allows us to analyze logarithm functions. So just remember as you work with the logarithm, the argument must be positive, and that will give you the inequality which you must solve. So what we're going to find as we get prepared for the calculus is that we're going to be solving a lot of inequalities. And sometimes we're not going to be solving a specific inequality. We're just going to figure out the sign of the function throughout its domain, and then pick and choose from that. So the problem will specify that we need to know all of the signs. And then the theorems will allow us to make certain deductions. So again, the process of using the BVs to solve inequalities will be something that you do over and over again. Now, let's look at some simple equations. We've already solved one before, but I'll go back to some of these simple ones. So for instance, what's a logarithm? Power of the base. So we'll do this. So we have, let's just say here, 2 to the x plus 1 equals 3. Okay, so we want to solve this, solve in the real numbers. And we'll do much more sophisticated equations as we continue, as we learn more properties of the logarithm, and you'll find them to be very useful in solving equations. But for now, we need the basics, because the basics will always allow us to complete the problem. So now notice the power of 2 is just x plus 1, and we have a 3 here. Now, I will be able to tell you more about changing bases and all, and I'll show you another technique which you can use to solve this. But let's now just use the definition of logarithm. We see that the power of 2 that equals 3 is x plus 1. So x plus 1 is a logarithm. So equivalently, x plus 1 equals the base 2 logarithm of 3. What's a logarithm? Power of the base. So x plus 1 is the base 2 logarithm of 3. Now we can solve for x by subtracting 1. So we have base 2 logarithm of 3 minus 1. And our solution set, we can just write in the curly brackets if we want. We don't always do that. Sometimes you just type it in or separate solutions with commas. Now, one thing that you might be thinking about is the fact that if the base A exponential and the base A logarithm are inverses, we get inverse equations. So let me write those down. So in this case, inverse equations, like we wrote down with the 1-to-1. So let's do it. So the first one, we can say the base A logarithm of a to the x, input equals output, should be x, where x is just a real number. We know that to be the case. Input equals output. And then, of course, you can flip it around because that won't matter. We can say a to the base A logarithm of x should also be x. Again, using the same independent variable because we enjoy that. And I guess we get a little bit lazy. And here will be x is what? A positive real number, so that the logarithm is well defined. So what we can see here is this mechanism will allow us to rewrite the 3. That is, we're thinking, you know, how can we rewrite this so that we can actually use base 2 and 1-to-1? So here's an observation. Let me write this in another color. So observe, and we'll just use this over and over. So we'll say 2 to the base 2 logarithm of 3 is just equal to 3. So basically I'm using 2. That is, notice base 2 exponential, base 2 logarithm, input equals output. So again, input equals output. And here I'm just using 3 in place of x, and in place of a, I'm using a 2. So we get this observation here, and you're thinking, oh, yeah, I like that. So now let's look at the equation with rewriting the 3 in terms of base 2. So we have 2 to the x plus 1 equals, now we have 2 base 2 logarithm of 3. But now the 2's are aligned, the bases are aligned. So by 1-to-1, we have x plus 1 equals the base 2 logarithm of 3. And if we solve for x, x equals the base 2 logarithm of 3 minus 1. What's a logarithm? Power of the base. We'll get exactly the same answer. So most students would say, well, if I'm going to go ahead and use my understanding of our definition of the base A logarithm, this is the quickest way to the answer. But you can also say this really wasn't too long, no longer than this, if we understand this. So this is a way to use the inverse nature of the base A exponential and the base A logarithm to rewrite the 3 so that it is now what? Written as a power of 2. The 2's are aligned. You set the exponents equal, and you get the same answer as we got here. So this is a way to kind of do a smoke and mirrors change of base, so to speak. You're just taking a constant and sandwiching that constant into a composition of inverse functions where input equals output. So this is just a sophisticated way of rewriting the number 3, utilizing the base 2 exponential and the base 2 logarithm, this right here. So it can be very powerful. Again, this is kind of like I say, an observation that is to show you what you can do with functions in their inverses. They really do turn out to be rather fascinating. Now, let's look at one more. So as you think about this lecture, you should go away with it with the following question. What's a logarithm? It's a power of the base. And if you do that, you've got the solution technique that's intertwined in our at least first definition of the base A logarithm. And we will find as we continue in the calculus and look at the more sophisticated rendering of the function, we get exactly the same results. So it's kind of like when you start trigonometry via the unit circle and get all those beautiful symmetries. And then as you move to the calculus and more sophisticated methods, you still get a very beautiful result, but everything you learned before still works, still consistent, but that preliminary approach actually gave you some very sophisticated techniques, which you will continue to use. So let's look at another example here. We'll do a logarithmic example. So we'll just do a base 5. So we have the base 5 logarithm of 2x plus 3 equals 2. Okay, what's the logarithm? It's a power of the base. So the power of 5 that equals 2x plus 3 is 2. What's a logarithm? Power of the base. So we say 5 to the 2 equals 2x plus 3. We're just keeping them fairly simple for now so you can get used to the idea of these new functions. So of course, 5 squared is 25. And then of course, just subtracting 3, we get 22 is equal to 2x. So x is just 11. So we have a solution set of 11. Now, another thing that's very important here is that as we get more sophisticated, we'll have to be very careful about this. You can easily just substitute and see that this is correct. But if we actually use certain properties of the logarithms, we will have to make sure that the actual values we get for x actually do solve the equation. If we square things or if we utilize properties that create quadratics, we need to make sure that the initial equation is actually solved. Here, it's very easy to see that that is indeed the case. What's interesting is that we think about when we were solving rational equations, and as long as we avoided zeros in the denominators for the values of the variables, we were in good shape. But if we actually duplicated one of those zeros, we would have to discard it. So you're going to have to be a little bit more careful with the solutions to logarithmic equations because of the restriction on the particular argument. Again, the argument must be positive. It does not mean that the values of x in the domain have to be positive. It just means whatever is substituted into the expression must have a positive sign. So remember, as you do transformations, you can move the parent function of the logarithm around, just like we did with the base A exponential. Very straightforward, very simple. But just remember, the key to working with base A exponentials and the base A logarithm are, number one, the exponent rules. We find those to be extremely important because we use those to manipulate exponential functions. And then number two is how we define the reverse path. So when you think about an exponential function and you move to the range and you come back to the domain by the reverse path, the goal or the target is the power of the base. So when we say, what is a logarithm? We say power of the base, because it defines the structural technique of a base A exponential and going in a reverse path. So there's a rich history of the logarithm. And if you have time to read about it, you may find it fascinating. But we will spend lots of time with the logarithmic function and the base A exponential, and that will be a prelude to the work that you do in pre-calculus when you actually start discussing the trigonometric functions. The marriage of the logarithms and the trigonometric functions is very interesting. And as you get to calculus, you will actually talk about the hyperbolic functions, which just bring into fold the natural logarithm and natural exponential in ways that are just fascinating. So again, take the time to get the basics of these functions, and you will find it to be extremely rewarding as you continue. So I hope that you've enjoyed learning about the basics. Again, remember, this is very important. We keep using the same techniques over and over. The arithmetic, solving equations, boundary values, multiplicities, figuring out positive, negative. That will be the case as we do our math from here on out. Get the fundamentals down. The fundamentals will allow you to solve the more complicated equations. Okay, I'm done for now. We'll see you later. Thank you.